Hello, everyone. For anyone who doesn't know, my name is Fandi Kalgi. I'm one of the lecturers in automotive engineering and particularly concentrate on the design and manufacturing. But I'm also the program leader for the BSc Automotive and Motorsport, and also I'm one of the academic advisor for UH Racing Autonomous and FSAI team, basically. So in today's workshop, we're going to talk about the machine learning, deep learning, which are part of really advanced neural networks. And we're going to have a brief introduction about what's artificial intelligence, what makes them quite unique, basically. We'll talk about really good neural networks as it were, particularly for the image recognition, video recognition. They're one of the best ones, which lots of companies that actually are investing a lot into that. We'll go through and talk about the convolutional neural networks. We're going to go through and learn how the architecture of that looks like. And we'll go through a few case studies. We'll start with the coding, and you will see that with the second course, we'll become less dependent on the coding, and to the last one, basically, you don't need to code anything. It's like a drag and drop. And you will see what you basically, the people think is quite new, like ChatGPT stuff. It's been there for a few years. And you don't necessarily need to write the code, and MATLAB already had it, part of the system that automatically write the code. So before actually I go through today's workshop, I'm going to find out what's your understanding of AI. How do you define AI? So if somebody tells you, for instance, I don't know, in this product we use AI, what do you think that AI looks like, or what that AI does? So you attended today's workshop by having some sort of understanding of AI, right? I want to see what's your understanding of AI, because then I can shape the rest of the examples that I will use based on your understanding.
Identifying patterns.
So it would be able to actually find similarities, what we call it the patterns, and would be able to help us to identify those. Yes, they're really good. What else?
Autonomous
Autonomous what?
software by learning.
So it will basically would be able to learn things and would be able to actually replicate those. You're absolutely right. So there's a learning feature of that. There is a finding similarities of pattern. What else?
Machine the human intelligence.
So you try to actually replicate what we do as a human. You're right. So which is why actually they use it, the artificial, because artificially they're going to go through the way that human are intelligent. And particularly when we talk about the neural networks, with the neural network, the reason actually we use them, we use the neural networks because they work the same as neurons in the brain actually work. What else? Give me some of the examples that actually you use with the AI as well. ChatGPT. Okay, what did you use it for? To do what? To write things for you, to search things for you, or to write a code? Which one? To do what?
Or be searching for something. Searching for something.
Searching for something, yes. So basically what it does, it's gonna go through same as what we as a human try to actually find the useful search. So we're gonna go through those keywords, we're gonna apply it onto basically the browser to get some sort of that software thinks you're useful, which are not necessary. And you can actually guide them. So work as an assistant. What else? So have you used any other software that actually had the AI into it, or any products that has an AI to it? Photoshop recently has an AI, so it would be able to actually generate images here, right? What else?
Text recognition.
Text recognition, yeah. Which would be able to actually replicate the way that our eyes would be able to read things. CNN.
On social media platforms.
Social media, so behind the scene, there's an AI algorithm. So that basically social media, within the AI algorithms on social media is much more like a pattern recognition. So they're going to go and find out the patterns of the way that we use the softwares, but they are not that much intelligent. So what they do, they basically have some sort of the virtual personas, and those personas, which we are quite similar. So probably, I don't know, they we have, I don't know, let's say 1,000 personas, and we are a mixture of those personas. So they're going to go through and match with one of those personas. They're going to learn based on those, and basically will predict probably what you will then do next in your search and so on. All of you assume that you have phones, right? And there are so many AI applications part of that. So there are lots of the machine learning, there are lots of sensors that would be able to learn from your habits, and it would be able to actually implement it in the software. Androids, iPhones, lots of them, they exactly know what time probably you wake up, and based on that, you can adapt the charging. So they start with a fast charge when you have a low charge, and will realize what sort of time probably you're going to wake up and put the last 5 to 10% of charge at the last minute. So basically, they don't have a continuous charging, and you're going to optimize as well. You're right. Great. So I'm going to go through a quick video. Hopefully we will have sound in here, which basically go through the AI and try to explain it. I found this one quite useful.
Artificial intelligence. So, HAL 9000 and Marvin the Paranoid Android. Thanks to books and movies, each generation has formed its own fantasy of a world ruled, or at least served, by robots. We've been conditioned to expect flying cars that steer clear of traffic and robotic maids whipping up our weekday dinner. But if the age of AI is here, why don't our lives look more like the Jetsons? Well, for starters, that's a cartoon. And really, if you've ever browsed Netflix movie suggestions or told Alexa to order a pizza, you're probably interacting with artificial intelligence more than you realize. And that's kind of the point. AI is designed so you don't realize there's a computer calling the shots. But that also makes understanding what AI is and what it's not a little complicated. In basic terms, AI is a broad area of computer science that makes machines seem like they have human intelligence. So it's not only programming a computer to drive a car by obeying traffic signals, but it's when that program also learns to exhibit signs of human-like road rage. As intimidating as it may seem, this technology isn't new. Actually, for the past half a century, it's been an idea ahead of its time. The term artificial intelligence was first coined back in 1956 by Dartmouth professor John McCarthy. He called together a group of computer scientists and mathematicians to see if machines could learn like a young child does, using trial and error to develop formal reasoning. The project proposal says they'll figure out how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. That was more than 60 years ago. Since then, AI has remained for the most part in university classrooms and super secret labs. But that's changing. Like all exponential curves, it's hard to tell when a line that's slowly ticking upwards is going to skyrocket. But during the past few years, a couple of factors have led to AI becoming the next big thing. First, huge amounts of data are being created every minute. In fact, 90% of the world's data has been generated in the past 2 years. And now, thanks to advances in processing speeds, computers can actually make sense of all this information more quickly. Because of this, tech giants and venture capitalists have bought into AI and are infusing the market with cash and new applications. Very soon, AI will become a little less artificial and a lot more intelligent. Now,
ChatGPT is one of those.
should you brace yourself for yet another Terminator movie live on your city streets? Not exactly. In fact, stop thinking of robots. When it comes to AI, a robot is nothing more than a shell concealing what's actually used to power the technology. That means AI can manifest itself in many different ways. Let's break down the options. First, you have your bots. They're text-based and incredibly powerful, but they have limitations. Ask a weather bot for the forecast, and it will tell you it's partly cloudy with a high of 57. But ask that same bot what time it is in Tokyo, and it'll get a little confused. That's because the bot's creator only programmed it to give you the weather by pulling from a specific data source. Natural language processing makes these bots a bit more sophisticated. When you ask Siri or Cortana where the closest gas station is, it's really just translating your voice into text, feeding it to a search engine, and reading the answer back in human syntax. So in other words, you don't have to speak in code. At the far end of the spectrum is machine learning, and honestly, it's one of the most exciting areas of AI. Like a human, a machine retains information and becomes smarter over time. But unlike a human, it's not susceptible to things like short-term memory loss, information overload, sleep deprivation, and distractions. But how do these machines actually learn? Well, while it may be easy for a human to know the difference between a cat and a dog, for a computer, not so much. You see, when you're only considering physical appearance, the difference between cats and dogs can be a little gray. You can say cats have pointed ears and dogs have floppy ears, but those rules aren't universal. Between tail length, fur texture, and color, there are a lot of options, and that means a lot of tedious rules someone would have to program manually to help a computer spot the difference. But remember, machine learning is about making machines learn like humans. And like any toddler, that means they have to learn by experience. With machine learning, programs analyze thousands of examples to build an algorithm. It then tweaks the algorithm based on if it achieves its goal. Over time, the program actually gets smarter. That's how machines like IBM's Watson can diagnose cancer, compose classical symphonies, or crush Ken Jennings at Jeopardy! Some programs even mimic the way the human brain is structured, complete with neural networks that help humans and now machines solve problems. Generations have long imagined the ramifications of AI, visualizing a society where machines seek revenge and wreak havoc on human society. However, the more logical and pressing question is, how will AI affect your job? Will it make your work obsolete? Just like the Industrial Revolution, it's not human versus machine, it's human and machine versus problem. The point is that artificial intelligence helps you accomplish more in less time, taking on the repetitive tasks of your job while you master the strategy and relationships.
I think that's quite important to know that the AI is not going to be basically against us to be able to actually get the job. So the job will change for sure. And it's very also the computer, was the companies invested heavily into the computer. Lots of jobs actually has been changed because of the computer. But what happened, the companies, they made it as a kind of like a need for these kind of skill set to be able to actually implement and use those computers. And I think this is the similar sort of era. Now the jobs will change, but the people who actually had the experience, they are the one who are going to train these basically AI systems. They are the one who are going to help programmers to program it. And the users will also need to contribute that AI by providing a data to it. So the jobs will change for sure, but the people will be quite successful. But they are the one who are actually building these architecture. They are the one actually can make application of that, which is why that there was a huge job in terms of the learning the AI and neural networks after ChatGPT been launched. But it's been ages we have AI. It's been ages that actually there are lots of really good scientists working on writing these programs, as well as what we call a pre-trained network. The network has been trained before, which we'll go through today. But this is your time to actually see which of the knowledge is already available to be able to apply in the world of engineering. Because in the engineering still, there's a huge area that is not touched. So the computer is not involved in a heavy decision making. One of the good examples is the autonomous vehicles, because quite a complex decision making. There are so many things goes through the processing to be able to actually car decide whether it's better to brake, whether to, for instance, the getting a speed, accelerate, read the road signs, read the objects, try to identify them, try to predict them, whether as a pedestrian they're going to jump to the road or not. And these are quite complex. So hopefully today with the 2-day lecture, you'll get some sort of idea about it. We're going to go through a few examples, but one of the networks that I'm going to go through today and talk about it is convolutional neural networks. Have you heard about the CNNs before? Except my students, which I'm sure you've heard about. Have you heard about the CNNs?
Yes.
Okay. Do you know any of the examples of where we use CNNs or not?
For image processing,
Mhm.
actually, I know they perform, or they expect they can perform more than other neural networks.
Absolutely right.
They are more prepared.
CNNs, yes, you're absolutely right. CNNs were one of the best neural networks right now that it can identify similarities, identify differences in basically images, and they perform well with images, but also you would be able to use it on the videos, you would be able to use it on the sounds as well, as long as you convert them to the image representations. And there are a few ways. With the videos, every frame per second, you would be able to convert to an image. If it's a sound, there are different ways, or a signal, there are different ways you can convert it. For instance, for my research project, I usually work with the biometrics, with the driver biometrics, such as the ECG, EEG, galvanic skin response, the respiratory rate, and so on. But because those are signals, I had to find a way to convert it to the CNN, and there are different ways. Simple one, you can actually picture screen it as it is, and CNN perform pretty well. And you would be able to also convert it with the scalograms. The scalogram is like a wavelet transfer function, and they perform pretty well as well. So recently, one of my basically projects into finding the heart arrhythmia, non-rhythmic heart rate, cognitive heart failure. We got 96% accuracy, which is a state of art. About the emotions of the driver, to find out the emotion of the driver, it's 97.3, I think, which is a state of the art. I'm writing a paper on that, and it's quite basically useful techniques that actually be implemented to the CNN to make it even better. Usually with the CNN, with a good CNN, you're expecting around 70 to 80% accuracy, and then it's your job to be able to actually improve that further, and you can reach to the 100% accuracy over there. For anyone who's interested about how we use the signals, these type of biometric signals into the car, we have two systems in the car: drive monitoring systems, DMS, which from 2025 become recommended by car manufacturer to implement in the car. So you have to monitor the driver, you have to monitor the health of the driver, the stress of the driver, the drowsiness, the level of drowsiness, the heart rate of the driver. And from 2030 become compulsory. And what the DMS currently does is basically work on the, what I would say, almost level 3 to level 4 of the autonomous vehicles. For the time that a driver is not healthy, so an ADAS, Advanced Driver Assistance System, is going to step in and control the car up to the time you will be able to basically come back to the same sort of status. And there are different studies we've done. When I used to work in automotive industry, we've done, for instance, if you have you're looking to actually get some sort of non-rhythmic heart rate, we ask you to breathe. And from that time, the car will control it. If you're stressed, the car will take control of the car, especially in the junctions, especially when you're changing the lanes, to make sure your level of stress drop. If you're emotional, if you're angry, probably you're speeding, the car would take control of your inputs. For instance, if you have a sharp steering turn, it will make a delay of that based on your emotion. I will try to actually change the emotion of the driver by playing the music, by changing the ambient light to make sure you come back to the same neutral status. And all of these, they are CNNs. And there are really good examples as well, which we will go through and explore. And you'll see that basically CNNs you're using on an everyday basis. There are lots of software that you're using, they're using the CNN behind the scene. But in order to actually understand it, I'm going to show you the architecture of that. Have a look at it, because we're going to go through every single steps of this, and we're going to explain what they are, how we can program it, and then at the end of the day, we're going to use a ready-to-use blocks for each of these. We don't necessarily need to actually write for that. Have a look at that. So basically, you will have an input. You're going to use something what we call the feature learning to learn the feature, to learn those patterns. And we're going to basically use those AIs to group them, find the similarities, find the dissimilarities, and then classify them. These are the three main stages that you will do. But in order to actually understand it, usually I use an example. So what is this one? It's a pen, right? You haven't seen it, you haven't touched it, you guess that it's a pen, right? So what do you think went through your brain to realize that it's a pen? Have you seen this pen before? No. So why do you think it's a pen? So it has a leads on. What else? What do you mean by look like? What are the similarities that you see? The shape of that, it will be able to have a tips, but even you didn't see that it had a tips or not, so you're guessing it. And also, if you have a look at it, it's not technically round, like it, basically triangular shape. Right. So what happened? You have a really advanced neural network in your brain that can find out similarities in basically milliseconds. And what you're aiming to do with the CNN, you're trying to achieve the same thing. So what we need to do, and what happened to you when you were basically toddler, you've seen so many examples of pen, pencils, and you had time to actually go them, touch them, first of all. Go through it, find out, okay, probably they're round, probably there's a tip, probably there's a leaf. And from now on, you don't necessarily need to see all of those features. Probably even if I show you these, still it will say this is a pen, right? Even if it's not the round, you will say still is a pen, right? And this is what we need to do with the neural networks, and mainly into the convolutional neural networks. We're going to give as much as data to the computer to be able to go and learn those features, which I will explain what are those features, these roundness, those triangular shape, those lids, and so on, and would be able to actually classify them. So in order to actually understand how the CNN works, so whenever you search for neural network, you see lots of these models, lots of these neuron-based models. With the neural networks in general, and particularly with the convolutional neural networks in here, which are one of the best ones in order to identify similarities and dissimilarities, or what we call the features, into the images, you will have an input. Basically, into the input, in the input layer, you have an image representation of your data. From that image representation, you're gonna do something which is quite like a magic into these layers, which we call the deep layers. And we're gonna then classify them based on basically the similarities and differences you will see in those kind of data input that you have. Right. This is basically general neural networks. What makes this CNN unique and make it convolutional network is what happened these basically what I call it the magic marks. And I will learn why it's called the magic, because you have some sort of level of control on it, and the rest of it is basically is magic. So what's going on over there? You basically, the input layer, gonna get some information, give it to one of these neurons, which I will explain what are these neurons. And these neurons, they're gonna do some sort of processing, some sort of calculations. And from that, it's gonna get that information and feed it to the other layer. And you will keep doing that up to the time you're confident that the network reveals some sort of features. An advanced CNN is when you have multiple of these neural network layers. More and more make the decision making more accurate, but of course you need the more computer power and performance. You need more CPUs, more GPUs, more RAM. And probably most of the computers cannot handle it, and then you will go to the area that you need the cluster computing for those. But in order to actually understand what they do, I'm going to talk about pattern. So what do you see in this image? What do you see? Spaceship, these ones, you mean? The paragliders, yes. What else? Yes. You will see the seeds. You will see what else? Yeah, there's a sky, there's a mountain, and there's sun, right? What is quite interesting, because we have a really advanced brain, an advanced neural network, what you will see, you see objects. But AI and neural networks doesn't see those. So in simple layers, in the first few layers, what they see, they become interested on edges. So, okay, quite interesting. I have an edge here, I have an edge here, I have an edge here, I have an edge there, I have an edge there. Probably I cannot find an edge, so I find a shape. And if I let it go, after that, you'll see, you'll find all those edges in here, and you see, I don't have anything. So what I will do, I add edge, 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 and once you have so many edges, it will convert it to the shape, which become like a round shape. And then you're gonna make that layer deeper. What it does, it's gonna become interested in these textures, because you're gonna put those edges together and come up with like a shape, which in here become textures. And then if I let it go further, if I have a really deep layers, then I will be able to see the objects. What's going on to your brain is quick like that. So it's millisecond gonna go through and find all those edges and put them as a shape and an object, and then you would be able to identify those objects. And this is the ideal CNN we're going to develop. And you will see today how we're going to be able to actually make a neural network that see objects rather than the shapes. But these are quite useful. These are really useful, especially for my student that they are working with the signal processing. You will see that it's quite interesting where the medical doctors look at to the ECG signals. In order to find arrhythmia, what we have like a PQRST, which basically is a peak into the negative and a peak positive peak and a peak to peak. This is where you will be able to actually see whether the person has arrhythmia or the person has a rhythmic heart rate. But what we found on actually one of the research papers, the network is not interested on the peaks to peaks, whereas with the old system, with the feature extraction, like the way that medical doctor look at it, you will look to the peak to peak, but AI become interested on the slope of that peak. Because it's interested on the slope of that peak, you can predict when the person gonna have a heart attack 30 seconds in advance. This is what basically Apple does with the Apple Watch. So before you have a heart attack, which no other medical doctor would be able to find out, the AI would be able to pick it up. Because what it realized that it goes through the features that you never think about it. And this is what hopefully if you have time today, I can go through that to see what kind of features the networks see. So each of these things that I was talking about, edges, shapes, object, and textures, we call it pattern, or we call them features. So in AI, you will see lots of pattern recognition, feature recognition, feature learning, and these are all these. If you have a really kind of advanced neural network, you will be able to actually see really quite complex objects. For instance, in here into the bird, you will be able to find out the eyes, you will be able to find out the tail. And from these, you will be able to actually find out what type of bird it is. Even you will be able to find out the gender of them as well, which is the PhD of one of my friends was on these and developed quite an advanced neural network for that. But I know it's quite confusing right now. You don't know how it works. Let's go through and understand what's going on in these hidden layers. I put basically a few examples of the number from the 0 to 9. So we have 10 different digits in here. And you will see that some of them are also written correctly into the basically 90 degrees. Some of them, they have some sort of like a 30 degrees rotation on them. Usually the way that we write them down. In order to find out how the neural networks, particularly in this example, a convolutional neural network, to be able to detect it, is we need to find out what each of these layers does. Each of these layers, we call them convolutional layers, right? So you had the input layers, you had the output layers, which was the classifier, and we had these deep layers or hidden layers. These hidden layers, if you use the type of convolution, we call it convolutional layers. If they are, for instance, if you're going to use the LSTM, become the long short-term memory networks, like RNN, recurrent neural networks. The difference between those, any information which pass through here, you also get it back. That's why they call recurrence. But the basic majority of them, they use a similar system in here. What are those actually? They are filters. And filters, they are matrices. So each of these, they're matrices. Matrix of 3 by 3, matrix of 4 by 4, matrix of the 5 by 5. And for instance, if it's a matrix of 3 by 3, we call it a filter of 3 by 3. And the beauty of it, and this is why we call it a magic box, is because we don't have control, and we don't want to have a control. We can, but we don't want to have a control of these values. It's a completely random number that we only control how many of these filters you're going to have in these layers, and what will be the size of that matrix, or size of that basically filter, which means how many rows, how many columns. More rows and more columns give you more basically freedom to be able to identify features. More of these filters help you to have more layers and make it deeper and deeper. But of course, once you make the matrix bigger, once you increase the number of matrices, then your calculation becomes more complex, which is why the computer needs more power. But what is actually going on in here is quite interesting. That matrix, let's say this is the matrix that we have, going to be applied on every single pixel size is correlated to the same thing. If it's 3 by 3, it goes by 3 by 3, basically 9 pixels of that image. And it will multiply, you can see it's really simple calculation, multiplication of the 3 by 3 matrix to the 3 by 3 matrix, and it will convolve, it will move on, which is why we call it the convolutional neural networks. Have a look at that in here. So to just give you an idea, background, if there is no color, is 0. The highest intensity of the color in here is the red is 1, and you reduce. For example, if you go with here, it becomes 0.9, 0.7, and so on. So if I have a matrix with this side, if I apply by matrix of 0, you will get 0, right? If I apply this matrix on here, which there is a color, I will get these. But have a look at to this image. This is a really, really good example. What do you see in here? I'm going to go back to it. What do you see in here? And compare with the original image that we had. What did it reveal to you? Have a look at it. It's a different representation of image for sure, right? What did it reveal for you?
It's much bigger.
It's a little bit bigger, yes.
More faded.
More faded, yes, which is the issue with the convolutional layers, by the way. Which is why if in case I'm gonna go and I create 100 layers, doesn't necessarily would help me because it became blurry and blurry and blurry, which after a period of time I don't see it. And this is the beauty of engineering to find out what layer we need to stop, and the rest of it become the basis of the computer power. So how do you write the number 7? So the way I'm gonna see whether I can write in here. I'm gonna go to the back slide in here, probably I can. So if I want to write the number 7, I will basically write it like this, right? And for me as a human, doesn't matter whether I'm gonna write it like this, always the same process for me. This is how I write it. What the network trying to find out in here, and if I want to use the old system uses the feature extraction. Before AI, we had feature extraction. We will help the computer find out similarity based on what the feature I would tell you. Whereas here is, that's why they call it magic box. The computer would decide what are the features. If I want to, as a human, would tell the computer what feature you need to look for, I would say, you need to find this line, you need to find this line, and you need to find this line. If you found these lines, then this is number 7. And it doesn't matter how you write it. Line, line, line. It's still what you consider as a 7. What we are trying to achieve in here is the same things as well. Line, line, line. Have a look at the intensity of that. It tried to reveal that intensity, and you will see it better. So this is why the basically convolutional layer does. For instance, in here, the same things. It will try to actually get basically representation of the smile, and you're gonna apply the matrix of the 3 by 3, and then you're gonna apply that 3 by 3 on these matrices, and then you will see at the end, if it continues, it will basically come with another representation of that kind of in a smile way. So it's just happening on that basically matrix. The same thing in here. For instance, if you're gonna find out how the A looks like, if I apply that basically concept of applying a filter of the 3 by 3 or 4 by 4, you will see you will be able to get a different representation. So what the CNN does, it will try to get a different representation of that image, and it will keep doing it until you will find out similarities and you will find out basically differences. So in order to actually go back to the example of number 7 in here, let's actually simplify it a little bit. I'm going to use 4 filters, and those filters are going to have a size of 3 by 3. In order to actually simplify and understand it better, let's agree that -1 represents black, 1 represents white, and 0 represents gray. What the network is trying to do in these 4 filters, for the first filter of the 3 by 3 going to be applied on the 3 by 3 matrix size of 7 by 7. Sorry. And you're going to reveal these. Have a look at them. So We said that in order to actually write the number 7, for me as a human, I will write it like this and add this, right? So the features for me is this one, the feature is this and this, right? The first filter revealed this one for me. Have a look at the white ones. This one, this one. Right? So technically, if I have a neural network with one layer, it becomes 3 layers. Input layer, one convolutional layer, and one output. It won't be able to pick up number 7. It revealed 2 features for me, but it's not sufficient. Right? I will make that network a little bit deeper, and now it's gonna reveal this part. You see that? Have a look at the white one. The white areas in here. Probably sufficient for the network, but it's not robust enough because if just seeing these features once, I'm gonna make that network deeper. Now we're gonna go to the 3rd layer. Look at these white ones. Now become interested in the bottom horizontal edge of that number 7. You see it in the back? So what it does, it's gonna add these and these, which means that you're gonna see these, but increase the thickness of that, increase the thickness of these is a repeated feature. And now become interested in the right vertical edge of this, which is this. Which means if I want to make a basically digit recognition for number 7 for it to work well, I need a minimum 4 layers. Probably if I'm gonna go with the further layers, it will help me with the different orientations, with different handwriting and so on. Because right now, probably what it's gonna learn that it's always a straight. So probably wouldn't pick up something like this, for instance. Right. So once you make it deeper and deeper, it will be able to understand. But do you understand what the filter does in each image? Is it clear for everyone or not? Yes? So the CNNs, they will basically try to find out those pattern and feature, and they're going to merge them together at the end. Once you use what we call a fully connected layer, you've got all those features back. And if you have a look at it, these are what we can reveal. These are what we call activation. We can reveal in the network what actually networks see, which is quite interesting. And usually we as a human, we try to interpret probably the feature they look at is what we are aiming for as well. So for instance, if you have a look at it in here, which is quite interesting. Do you see these? Do you see the edges in the corners? Have a look at how network pick it up. The beauty of that network completely forgot about the pattern. Have a look at this. Do you see that? It completely forgot about the background, just keep those features. And how do you think the network would be able to do the same? Have a look at these, right? The circle shapes. Have a look at these. It completely forget the background. What do you think it will forget the background? Yeah, so we'd be able to detect edges. Why do you think actually it will forget the background? Think about the concept of that multiplication of the 2 matrices together.
The same.
Changing, not the same. Same or changing. So, and that's really important because you'll find out there's something keep changing every time. Probably it's not important because it keeps changing. Or some of the values always is similar, which means that this is really important in the data preprocessing. If I have, let's say I'm going to find out the emotion of the person. A person which is happy, a person is sad. How do you find out it? From what feature through the face you will see it from the facial expression, right? So probably is a happy, always have like lips up. So if he wants to use a feature extraction, the old system, probably I put 1 point in here, 2 points in here, and 1 point in here. And I will see if that 2 points goes up, probably I'm laughing, and probably it goes down, you're sad, right? But now, if I go through the network and then give the images that when I'm happy, always I'm sitting like this, I'm happy. And when I'm standing up with this background, and let's say I'm aggressive or angry, it right then become interested on my lips, it become interested in the background. Probably since whenever I see something in the background, the person is sad, probably the person actually has, let's say, a white background, probably the person is happy, which is a major problem. The issue with the computer and AI, which is why everybody is worrying about, is GIGO, garbage in, garbage out. If you train them wrongly, it will learn those and respond wrongly as well. And that's the major, discussion about these computers, the kind of data they're going to feed those to them. I know AI, it's there in terms of the ethics with the AI is one of those controversial topics. AI can be racist, and there are some examples about it. So many examples on that they've seen the AI become quite racist. AI can do basically the really kind of ethical decisions as well, and these are all based on how we train them. So, for instance, in order to actually give some sort of idea, for a period of long time, if you upload the face of the person that had the colored skin, it wouldn't be able to actually recognize them whether actually they're human or not. Why? Because all the data that they've been used, they've been trained with the white people. So that's why the network never seen these as a feature, never look at those, and never exist. IBM recently had a court case, which was a group of women actually took the IBM to the court that when they apply for a job, they won't be able to actually be selected to go to the interview. What happened? The IBM system so usually with the CVs when you upload, they're going to give you a point. So it's like a point-based system. They're going to give you points based on the keywords you use and so on. Based on thousands of people that apply for jobs, men used to basically show off their skills by putting so many kind of skill sets and soft skills, put so many keywords. Girls usually didn't put it, right? So the network become interested that once you use these keywords, you are probably good candidates, and you select those. Didn't care about the genders at all. But eventually, because the girls didn't use those keywords, they didn't go to the interview. And the IBM had to go and defend. That wasn't us. The data trained the AI in that way that almost no girls would be able to actually pass that training. Because what happened, realized, okay, that's simple, right? And I go through the keywords, it's better. If I concentrate on the genders, men's, is basically I can easily select them and I can put that group away. Didn't care about what is the gender because it doesn't understand it, but I found out similarities between them. It can become really hard in terms of decision makings. This is what's particularly if you're working on the autonomous vehicles. It's one of always the controversial topics. Before COVID, I went to the House of Parliament and had a talk in one of the AI work groups about the code of conduct, about the ethics, and about the morality. There's a big discussion right now with the car manufacturers that let's say you're driving a car on autonomous mode and somebody jumped to the street. So what the car needs to do? So the car needs to go through the process. First option is braking, but they will have a look at it. If I brake, what happened to the rear car? Would the rear car, they're gonna hit me based on the speed? If that's the case, probably it's better to actually overtake that person, to do a maneuver and overtake that person. Is it better actually for me to just change the lane quickly? And if I change the lane quickly, what's the projection of the car behind me and so on? So it's still is a quite complex situation, but it's a really simple situation for AI to decide, right? But now, if is a pedestrian jumping in front of you, cyclist next to you, what would you do? In reality, so for instance, if you're a driver, what would you do? You're gonna brake, right? But you don't know if you brake, the car behind you're gonna basically hit you and gonna still hit the pedestrian, right? So with these decision making, you're gonna go through the situation which we call it the morality. In reality, you might kill both of them. You might have a really bad maneuver as a human, you would be able to kill both of them. But once you go, you're gonna train robots. You're gonna train AI and see whenever you see that situation, you have to do something. Let's say if you agree, the safest option is to kill that pedestrian. You're teaching AI that you should kill that pedestrian because it doesn't do any kind of calculation. You just see this is the order you give in that situation. This is they have to follow it up based on the patterns. And this is quite a complex topic. It's if you're interested. Let me see whether I have any. If you're interested, there is the. Actually, see it in here, so I can load it for you. It's called Moral Machine, and Moral Machine is started by MIT, and it still is one of the really advanced database in terms of these judging. So what it does, it gives you different scenarios and will tell you as a human, who would you save, who would you kill? And the result that actually they revealed is quite interesting. Let's say I'm gonna go with the next question. I have to decide which one I'm gonna say, which one I'm gonna. So what basically, because if the people they're in here, what you will do, your car needs to go there, right? Simple. So unless you're really amateur driver, you go straight to them. So we're gonna change the names, right? But now gonna change this. How about animals? What would you do? Still, I'm probably gonna go there, right, to save those animals. And now we're gonna go to the situations that basically you will still are gonna go with these. Okay, who would you hit now? Old people, young people. You have to kill one. You don't have any other choice. Who would you hit?
Mine's good.
Of course you will break, but then if the brakes didn't work, old people. So let's go with one. I don't, but let's say I will do the young one. So, but now it's so with this one, it's simple. I'm gonna go with these. Now go with the situation, the same sort of things as well. It's what do you think is the difference between these two? One is going toward the red light, one is going to green light. Who are you gonna penalize? The one who didn't bait, or the one who basically going through the green light? Red light, right? You're gonna penalize the one who's gonna go through red light. You're teaching AI, by the way. Bear in mind, this is at the end. We're gonna tell you you're teaching AI. So I'm gonna say penalize the one actually didn't stop. And now I'm gonna go to the crazy situation in here that two people followed green lights. Two people didn't follow the green light. They're going to the red light. A toddler, an animal. Who do you hit? Yeah. So this is quite a basically unfair, biased decision. So what we call it, basically, you're gonna penalize the one who basically done a correct thing. They are going through the green lights, but you're gonna go to the favor of the group of people that doesn't follow those rules. Think about the biggest scale. So you're still gonna penalize the one actually following the rules, which means that if you're gonna train AI like that, the people get used to, they don't necessarily need to follow rules. As long as you have a larger majority, the AI will do a favor, which is what happened with the Intel about the gender-based. They basically went toward the majority of the people. And you're gonna go to the crazy situation when there's a cyclist next to you, when there's a toddler in front of you. But the result they revealed is quite interesting. They went over, I think, 7 or 8 million votes so far. And so they realized that the countries and different cultures, they have the different decision makings. In Africa, they're gonna prioritize the elderly people. In French, they become gender-based. Usually they go in favor of the ladies. In USA, they're gonna go in favor of the young people. So it's become really hard for you as a programmer how to train cars, right? Which is why we don't have level 5s car right now, because in terms of decision making, it's quite a complex situation to do. Tesla, I think they've been quite brave enough to go with that in their autonomous decision making. They're gonna protect everyone except you as a driver and passenger. So there's a disclaimer. If you activate the autopilot 4, they will tell you, okay, in that situation, the car gonna go to the hot shoulder to protect everyone. So basically the car in here is gonna hit to the side to protect everyone, but it's our engineer responsibility to protect you in the car with the airbags, with the the seat belts. So that's their responsibility to actually take care of it. But then I don't want to get involved with the lawsuits, because bear in mind, if you hit any of those, you actually murder them. Because in a situation when you're driving, you're not murdering. It's out of control. But in here, the AI already know that who you need to kill, which is quite a big topic. Have a look at the neural machine. It's quite, and there's so many papers around it. It's quite interesting. And of course, you can contribute to that decision making, because someday one of the car manufacturers going to get the data from MIT and work at it. But so AI is quite a basically big topic. It's not simple to say how you're going to do it. But what it does, it's going to go through features. And those features, which we call it patterns, they're going to reveal the similarities and differences. Once you have a really advanced neural network, it would be able to see things like us as a human. For instance, I really like this example about the way that we look at the dog, we look at the, the ears, the eyes of them, the mouth of them. Funny enough, network also see like this as well, but doesn't care about the rest of the face of the dog. See, it's in the eyes, still the lips and so on. But let's go through and understand how it works first, and then we'll start the coding of that. So in the first layer, in any neural network, you will have an input layer. Particularly with the convolutional layer, with the convolutional networks, that input layer should be an image. So a CNN expects you to have an image. If you have a video, you have to convert an image. If it's a sound signal, you have to convert an image. That image has three information that the CNN is looking for. The size of that image, X and Y, which will give you, let's say, I don't know, 30 by 30 image, 140 by 140, 125 by 130, whatever, X by Y, right? But the image also has a depth, and that's really important. That depth is the channels, what we call the colors, basically. If it's a RGB, what's the channel for RGB? 3, right? Red, green, and blue. So most of the, by the way, CNN works pretty well with the colored images because each image is technically 3 images for CNN because it's gonna separate red, green, and blue, which is why it becomes heavier and heavier. So you put the X, Y, and the Z, and basically if it's an RGB, you're gonna put basically the channel. Bear in mind, if you're gonna use the grayscale, the color is 1, right? It's just the gray because the white one is the white is a 0. So once you have those, and this is really important, if you don't define this well, the rest of the layers, because it's the matrix, you're gonna try to find a 3 by 3 out of that image, doesn't work. And you will see that you usually get the error with it. So now we're gonna go with the feature learning part. So now we're gonna go through and do some sort of magic in here to be able to network see those features. The first one is a convolutional layer. What was a convolutional layer does? Absolutely. So it's the filters, and those filters are going to apply on those images, right? So what you need to do, you need to control the filter side. Even you don't need to control the numbers of that filter. The filter side, 3 by 3, 4 by 4, 5 by 5. Usually it's recommended to start by 3 by 3. It's a recommendation. You don't have to, you can go with the 2 by 2 even. So 3 by 3 is a recommendation of the filter size of the CNN. Most of them start with the 3 by 3, but also there is another thing as well. See whether you can see my full slide in here. And in the slideshow, I'm gonna put it again so you will see. Okay, yeah, that's better. So you will have a 3 by 3, and also you have to say, okay, you have a 3 by 3 filter. How many of that filters do you want? Right? So in each layer, you have to say how many of the filters you want. So it becomes the number of filters. More filters, more advanced, more computer power needed because there would be more calculations. And also the memory become bigger because bear in mind, you had one image, you're gonna apply one filter, you're gonna get one image out. One image, I'm gonna apply 3 filter, you're gonna get 3 image at the end. And bear in mind, once you become deeper and deeper, you start with, let's say 100 megabytes of data, you will end up by 1 gigabyte of data. You start with 1 terabyte of data. Usually you're dealing with the 10 terabyte of data, which computer cannot handle. You doesn't have enough RAM, it doesn't have enough memory, which is one of the major issues with the convolutional neural networks, because you get more example of that image. And also you're gonna have padding 1 or not. Do you know what's padding? Anyone knows in here from computer science know padding? Yes, so with the padding in here, with the neural networks, is the corner of the images, right? The corner of the images, if there's a feature hidden in here, let's say this is this thickness, and let's say in here, this thickness is important for me, the AI probably wouldn't be able to pick it up because it's quite in the corner and will consider as a background. But if I want to take it, I will add a padding. That padding is gonna extend that image, so then they reveal that line for me. For instance, if I want to show it, in here, do you see that's this is quite important for me. That line is quite important for me, but it's quite close to the edge. What I will do, I use padding. So I will increase the thickness, and this one become white for me, so I can't see that feature. Most cases you don't need padding, so you use a one. One means that same size of the image, same size of the convolutional layers network, the image as well, right? 100 by 100, you get a 100 by 100 image. If I use a padding of, let's say, 2, you're going to double up the image, so it reveals the size of that for me. But in most cases, you don't need it. And also, we try to get away from the padding because you don't want to increase the size of the image. That will increase the computer power required. So you have the input layer. You basically apply those filters on it. And those filters are going to give you random numbers. You now come up with this situation that you have so many numbers. Not only you have so many numbers, you end up by the situation that you convert that one image to 3 images, 10 images, depends on the number of filters. So you go with the situation that your computer is going to show you error that you're out of memory. So what you need to do, you need to basically try to simplify that for computer. One of the ways you can use it is what we call the batch normalization. What we do, first of all, I think the computer now in this situation become a little bit lost because you come up with the different values, so many values, and you don't know which one is important, which one is not important. In order to do it, what we're going to do, we're going to say any value which is above 0, keep it, because that's the intensity of color. Do you remember that, like number 7? Anyone which is 0 and below, forget it. It's the one that keeps changing. It's the one that's background. And I don't need it because I'm going to simplify that for my memory. This is what we call a batch normalization. And one of the best one is ReLU. What the ReLU does, exactly the same thing. If it's 0 and above, keep the value. If the value is below 0, forget it. I don't have computer power. Probably is a background. Probably, because you don't know. You still might lose some of the data, but at least you are trying to simplify. So every convolutional layer always comes with a batch normalization of the ReLU layer, always. Otherwise, you become out of memory. Which is why in the structure, it says input convolution plus ReLU. Convolution and ReLU always together because you convolve it, you make so many data, you're going to simplify it. After that, you're going to go with the, again, a situation that is still, you will end up by so many still basically examples, so many numbers in here. We're going to help to reduce that load onto the basic memory of the computer. And this is what we do in here by the pooling, or what we call the max pooling. What the max pooling does, to be honest, is quite interesting mathematically. So let's say I'm going to use the max pool of the, I'm going to go with this one first, you will understand. So let's say you have, what's this? 1, 2, 3, 4 by 4 image, 4 by 4 matrix, right? Each image is a matrix as well. And what I will do with the 4 by 4 in here, I'm gonna go with this, but then I will go with another simple one. I'm gonna use, forget what it's right, I will talk about it. I'm gonna use a max pool of 3 by 3. Max pool of 3 by 3, what it does, the 3 by 3 matrix, gonna go and apply it on this image. So this is 3 by 3, right? It's gonna go through, we have 2, 3, 4, 1, 5, 3, 0, 4, 2. Which one is the largest number? I'll put it here. Then I will move on to the next 3 by 3, 3, 4, 0, 5, 3, 2, 4, 2, 3. Which one is the highest number? 5. I'll put it there. So what I'm trying to do, I'm gonna get rid of all those numbers that they're low. Why? Low intensity means that they're not important because it's not a solid color, right? This is what I will end up. I have a 4 by 4 image size, 5 by 5 matrix. I will end up by 4 by 4. But all of these are really high intensity, which is why if you look at to the face of that dog, you forgot complete about background. Just pick up the eyes, pick up the eyebrows and the mouth, right? In order to also simplify it, what I can do, I can use something what we call a straight of 2. First of all, is a 4 by 4 matrix image. I'm gonna reduce it to a 2 by 2 image. I'm gonna shrink down that image. Doesn't always apply, especially if you have, let's say, if you're working on the images from the skin cancer, skin which has cancer, so probably it's not good to actually shrink down the size of the image because you need that. But if you're looking into the face of the person, probably you don't care about the size. The features are unique features, right? So this is what do you need to decide? For instance, for the FSAI, for that decision making, you can shrink down because technically the quality of that cones that you're looking at is not important, right? So first option, I'm going to use a stride of 2, which means that reduce it by 2. 4 by 4 will become 2 by 2, right? Now I'm going to apply a max pool of 2 by 2 on it. So I'm going to go here in here, 2 by 2, highest number 5. I'm going to put it there. I'm going to convol. I'm going to move on. Highest number of these 4. What's the highest number of these? 4. And what's the higher number of 6? This is my new image. Shrink down. I got rid of all the information, much more simplified. And you will see that your own time, remove max pooling and see what it does with your computer. Your simulation takes time. Most of the time, you will say that you're out of memory. And bear in mind, this is very still in first layer. So, and if you're going to have 10 layers, basically you will end up by having one image, 1,000 representation of that. And you don't want that to happen. Because usually you start with 100 megabytes of data, minimum 100 megabytes of data. It will end up by having gigabytes of data, which the computer cannot handle. Ideally, in the autonomous world of the autonomous cars, we are dealing with the terabyte of data as a starting point. You will end up by 10 to hundreds of terabytes, which there is no way you will be able to communicate it on the cloud or would be able to actually store it on the cars. So you keep repeating these. The rest of it is keep repeating. You keep repeating this process until you're confident you learn the features, which is the beauty of us as a good, basically, AI engineer to find out how many layers are required to be able to actually find the features same as we as a human would be able to see. So always the convolution layers. So basically it will be conv layer, it will be ReLU layer, it will be max pooling. Is that clear? Yes. There was the exam question for the MSCs for last year for AI. Then once you do that, once you keep repeating these, you're gonna say, okay, I end up by getting so many information. Now what I need to do, I need to bring all that knowledge to the questions, right? Let's say you basically each week, let's say you're gonna have 10 lectures. Each lecture you're gonna learn about something. Now we're gonna go to an exam. What you need to do, you need to bring all that knowledge from every single lecture into one place. All those features into one place. This is what we call the fully connected layer. The fully connected layer, what it does, it brings all that knowledge back to one place. And that one place gonna go and group those features together. The group that you will have, which we call it output, should match with the group of the input. If I train the, let's say, the computer to find out whether the color of the objects, let's say, are black and white, and we don't care about the object, it's just become color sensitive. I need to make 2 separate folders, white images, black images, right? One is go to the fully connected layer. How many output I would need to have? 2 on. Yeah, absolutely right. Because this is what we call it is a supervised. So are already classified. We have unsupervised as well. Unsupervised, give them these, and the computer needs to find the features. This is a completely different way of doing it. Gonna go with the supervised, it's the supervised. But what's going on? We have an unsupervised feature learning in here, which is what we call the magic box. Deep learning, that's why everybody call about it, because it can reveal things that you never think about it as a human. Let's say for project, we're gonna go through some of the projects. For instance, if your project gonna find out the heart rate of the person, in your groups, you have to find out what groups you're gonna have. Normal heart rate, arrhythmia, cognitive heart failure. In the FSAI, if you want to detect the cones, you don't need to care about the cones. It become a color sensitive. You're going to have 3 classes, basically the yellows, blues, and orange. And each of them also has some sort of the banding around them, the white or the black, basically color strips around them. If you want to make sure that actually you will see the cars or trucks or the cyclists, I will see, okay, what classification I want to do the car to decide, let's say cyclist, car, bicycle, what else? The animals, pedestrians. So we'll have 5 kind of class of input, 5 outputs. This is very defining the fully connected layer. So you define, you bring all the knowledge back, how many groups you want it to do. So what it's trying to do, it put all the features, go back and check, these features coming from what category? And put them in those categories. So whenever you see that feature in this category, this is this. Is that clear? You might have situations when basically two categories, they will have two similar features. And in that situation, what would you do? Once we do the coding, I will go through it, but what would you do in that situation? Two classes, they have two similar features. What happened, first of all, it's gonna misclassify them. So let's say from class 1, gonna keep classified as class 2, or class 2 keep classifying as class 1. So in order to remove that feature, what would you do? First, you need to go to the image to see you as a human. We'll find out those similar features. And if you see those similar features and they are really a feature, that's fine. You don't need to touch that image. But sometimes you will see that's basically similar feature. They are not actually a feature. One of my students recently was working on the driver attendance, driver awareness system. And he had two situations. When the person is drowsy, when the person actually looking backward to try to grab something, and when the person was like basically drinking. And we realized that the keep drinking and the normal distraction going and leaning backward to grab something been misclassified together. And it worked a lot to make the network deeper and deeper to find the features, but always had a low accuracy on those two. When I removed those two classes and merged them together, the accuracy went over 90%. When we had them as a 3 separate classes, we had less than 70% accuracy. When I checked the image, it was quite interesting. The person was drinking like this, and the computer didn't know because the person didn't look to the front, so it's distraction definitely, but didn't know whether the person gonna lean backward to grab something or drinking. So what we eventually had to do, we had to basically remove those images when the person looking at the back because it was similar features, but technically it's not a feature because the person is drinking. So the network should become interested when you're grabbing something in your hand, basically. So once you have those, again, to make sure everything's correct, and you end up to simplify these, we're gonna normalize it one more time. To end up by having a few numbers which are basically bigger than zeros, and the numbers that are less than zeros. Again, we gotta normalize everything, especially those big ones, because those big ones, let's say you have a number of 2, another image you have 4, another image you have 5. So you have to find out which one has the highest intensity of the color overall. So you normalize it. And this is what we have, softmax. And at the end, you will have your own classification layer, how many outputs you're gonna have. That's it. So basically in all the coding you need to do and all the even the drag and drop method, you basically have an input layer. You will have the convolution layer. You have a reader layer. You have a max pudding. You keep doing it until you're fine, fully connected layer, and an output layer or classification layer. That's it. So what I want you to do, I want you to go back to your computer. If you didn't install the MATLAB on your machine, that's fine, because I know that some of you had issues with the license. Go back to the MATLAB, launch the MATLAB, and I want you to please open up this link. What I can do, I can either create a QR code for you on this. Let me quickly create a QR code so you can, or even QR code doesn't work. So can you search for this? Type create simple deep learning neural network for classification. I put MATLAB. I want to go through these. I will send you this slide because I don't want all of your email, so I'll send you this slide. Once you open up the link, let me duplicate to make sure it's correct. Did you search what they found? I don't need to. And for now, I don't understand. Just search for this. So you will see the one that actually has few numbers. Is it what you're saying? So can you please go through them, read them, and I'm going to quickly explain what is going on. Just use Google for speech. You can search in here as well. Search for what was the title? Very simple deep learning. For class. Okay, have you all opened it up? I've done it as well. Everyone, open this one. Open this link. Okay. So probably hard because I have to look at from here. So what you're looking in here, this part of the code is you don't necessarily need to even do it. You will do it in here to just load. But what it does, it's gonna just load the data from the MATLAB library. If in case you're programming for yourself, you don't need to actually do that because you can drag that folder and easily put it in the MATLAB. You put load and you put the image. But because you're retrieving that data from the MATLAB memory, you need to use these code. But otherwise, you don't necessarily need to do that. The other part, this one. So what it's trying to do is going to just show you some random numbers. Even in terms of coding, you don't necessarily need to do that. What's going on? It actually starts from here. This is where you make that architecture. What I want you to do, go through and do all these codes, but also try to basically read these and try to learn them and raise your hand if in case you have any question. I want you to understand it first because the first one is with the coding and then we're going to become less dependent on the coding. Let's start putting in the MATLAB. We're going to start a training together. And also I got a response from the IT. Anyone who has the MATLAB license problem, would you be able to actually give me your name and student ID? So I can actually send it now. Yeah. Do you have your? I need to basically take paper and write it down. Let me see. Put your name, sending, and email address. So put your. I'm gonna give this for anyone who has a MATLAB license issue. Please write down your name, student ID, and your last email address, so I can send it to the IT and they can retrieve the account. Or even calling for, you don't necessarily need to talk. You can just copy and paste each line over there. But try to understand what it does. Open up the MATLAB, try to copy and paste those and see what it does. First and for the first part, you're gonna load the image from the MATLAB library. Gonna open up the MATLAB in here. I don't want to. Let's see. Restart the MATLAB. So you can see what it does. The first part of that code, it's only gonna bring me basically the link or a pathway to the source. And even if I go in here, you'll see that it will open it up. If I go in here, technically this is just reveal where is the image is being stored. So if I open up the directory, and if I go to that folder, you will see these are the numbers, right? These are all those images, the number ones, number twos. So that part of the code was just revealing that folder for me. So if you had that folder in your desktop, you could see load, C, and a slash, I don't know, your user and slash the basically the data that you have. That's it. You don't necessarily need to do anything else. That's the first part. So the second part was to just get the basically a random images by having basically four rows, 5 columns, just show the random. This is just for you to get some sort of idea about what data you're dealing with. You don't necessarily need anything else. But if you already have the data, if you know your data, you don't need this. This is just like a image representation of that, and this is what you should get. The only thing probably I'm worrying about this. So this will help you to get some sort of idea whether you have a good data, not good data as a human, whether you would be able to see similarities and differences. One of my major concern on this one, if I wanted to actually do this as a project, would be one number. Which number do you think would be my concern? No, why 4, why 3?
197. 9 maybe.
9. Because 9 and 6, if they rotate up to a certain limit, the computer would be able to pick it up whether it's a 9 or 6. Especially because they have a rotation in here. I can see the rotation in here. So for those, usually I will go through to make sure I don't pass in 6. I don't pass that basic 90 degrees move, because I will end up to go into the other class. This is what usually be my concept. So after this, let me close this one. I don't need it, but if in case you want to save it, you know how to save it. You can save, or you can save as, and then you can save it as an image. If in case you're gonna put in your report, or you can save it as a MATLAB figure. I don't need this. But what is important for me, I have an image data store in here, and I have my path to the basically the data. That's it. I don't need anything else. So I'm gonna go through the code again. This one, it's gonna tell me how many images that I have. I don't necessarily even do that, but I will show it to you, and I will also tell you if you don't want to use coding, how you would be able to actually do it. So if I go there, it's gonna tell me I have 10 classes. Numbers are 0 to 9, and each of them I have 1,000 data. Try to get used to that. a neural network to be able to perform well in each category, ideally you should have a minimum 1,000 data. And that's really important. So if you don't have that 1,000 data, probably your network will come up with two situations. Either it would be able to actually decide well, or if you have less data, we call it overfitting or generalization issue, which means that it becomes quite interested on some features that doesn't necessarily apply to the bigger applications, especially for vehicles, for instance. If I train it with 100 images, I'm going to put it on the road, it's quite risky because you're going to see the examples that wasn't in that 100. So I need to make it bigger and bigger. There's another thing which is really good in here. Do you see all the classes there are 1,000? What we say, we say we have a uniform number of the data, which means the network wouldn't become biased. If you have a uniform number of data, the network doesn't become interested on any of these numbers. But let's say in each category, I have 100 images. One category, I have 1,000 images. Network become biased toward that category which has 1,000 images, because realize it's quite interesting. It realize if I keep misclassifying at that class, somehow because you have more images over there, you will come up with a higher accuracy. So that's why you need to have a uniform results, because you're going to test it, you keep testing it, right? Because you have 1,000 data, your test, most of them probably comes from that category because you see so many examples of that. That's why you should go with a uniform. But even for that part of the code, if you didn't have it, you don't need, because if I go to that folder, if you're not a coding person, if I go to each category and if I go to the properties, you will see that there's 1,000 files. If you're not into coding, you don't have to use coding. You can manually go to each folder and have a look at it, how much data you have in each category. So now from that, so far I didn't start coding. I didn't start building CNN yet. The main part actually start from here. So first we said that you have an image, right? We're gonna see from that database, it's IMD, read it, and also show me the size of that image. This is really important for you because size of that image, you're gonna help you with the calculations. You see that in here, it says image input size. You should know the size of that image, right? If you don't want to use code in here, I'm gonna use code. I'm gonna tell you if you don't want to use the code, what to do. If I put it there, 28 by 28, right? How can I find out whether the size of the image is 28 by 28? If I go to that folder, I'm gonna go and open up one of these images, properties. It's gonna give me the 28 by 28. What is quite important into the CNN? All images must have the same size. You cannot have a 28 by 28, some of the images 30 by 30. If you're having that situation, you have to go with the crop function or resize option before to make sure all of them they have the same image size. And to be honest, 28 by 20 is quite a small. This, you can see it. Because it's a really simple number, it's fine. But if it was the face of the person, probably the network wouldn't be able to even perform because it doesn't see any of those edges and so on. I think that was the issue last year with one of the data sets for the comps. It was quite a small. Okay, so still we haven't done anything special yet. And in here, what do you think going on in this line? Yes, absolutely right. So what you need to do, you say, I have, in this case, 10,000 images. From that 10,000 images, you're gonna say, how many of that data you're gonna use for training? How many of that data you're gonna basically use for testing? What's going on in here? Let's say you have basically a revision session. I'm gonna give you 20 questions, but I cannot use that 20 questions in the exam. What I will do, I will say out of that 20 question bank, probably I'm gonna put 15 questions to go through the revision so you learn from me. 5 questions I'm gonna keep it for exam. This is what's going on in here. The combination you use, this combination that's important. You either use 80 for training, 20 for validation, 80% for training, 20% for validation, or we wouldn't go below 75%. We never go below 75% for training, because for training you need more data. Or what you can do, you can go with a 75, 15, 10 or 80, 10, 10, which basically 80% go for the training, 10% for validation, 10% for testing. Validation, I will explain once you're gonna go through the code. While you keep learning, gonna do a lucky mini quiz to make sure the network learn. Because if the network learn we will realize actually once the network accuracy is low, we're gonna go back and retrain. And you're gonna go with the final exam, right? In here, what it does, 75% of that you're gonna keep for training, and the rest of that gonna keep it for validation, and make sure it's randomized. This randomized is really important because depends on how or who collected the data. I've seen so many examples that they went to the different people, get the data. Probably they started with the, I don't know, male on one day, female on another day. If you're going to train the data with the male data, test it on female data, features are different, probably. Or I had a data set that's my student, he done a project with me over 6 months. And especially in drag and drop, it's the one tick icon you have to put it at random. He didn't randomize it. What happened in the car, the database was, majority of the data was in the morning, some data at the night, but they collected the morning first and they put the night at the back. So he was learning with the day version, testing the night version, and the performance was really, really low. But he never showed me the random number and the random basic example of images, so I didn't see it. But under the Wi-Fi, I realized actually that was the issue, because it saves so much time to know that if you randomize it, you will learn both data together. So make sure randomize. That's it, just the group the images. So I'm gonna copy this as well. We're gonna put it in here. So what you can see from that image that we have a 28 by 28 image, some of them that have been classified as trained, some of them has been classified under validation. And in order to actually see what are those images into the new MATLAB, I can go with the DMS train. This is my training data. Out of 10,000, 7,500 went to the basically training because I said 75%. And if I click on there, open up in here, this is the basically link to each of those images. Right? Is it clear what we're doing in here? Yeah. So by the way, these codes, you can use the same sort of codes. Even last year I was saying use a simplified CNN. You can use these CNN. It gives you really good accuracy. You don't need to, you just need to put a different data set. That's it. So what you're learning, if you change the data set, that's it. The rest of the code, you can keep it as it is and give you good accuracy. And we're going to go through and give you really good examples. That's what you basically need to do. You just need to train it with a new data set. You still get a really high accuracy. So once we've done that, I'm going to go to these. Now we're going to start building the architecture. First is the layers. The first layer was the input layer, right? The input layer is size of image X by Y by the depth, right? 28 by 28. What was the depth? Because it was grayscale, 1. Then I'm going to go to my convolutional layer in here, right? Convolutional layer. What does it mean? A matrix of what size? 3 by 3. How many of filter? 8 filters. Should I use padding? No padding. It's basically the same padding. So the size of image, that 28 by 28 will be kept at 28 by 28, right? Then after each convolution layer, what will we have? We will have a batch normalization, and we have a redo layer. Always you have these. You remember that it was saying conv with batch normalization or plus redo? And then after that, I will end up by how many images in this condition? 8 different representation of that image. So I'll go with the situation I was probably most probably going to have issue with the memory. In order to simplify that, I'm going to use a max pooling. Right? Do you remember the max pooling? Select the highest number for that matrix. So I'm going to use a stride of 2. What does it mean? If I have a 4 by 4, I'm going to come up with a matrix of 2 by 2. And my max pooling going to be matrix of 2 by 2 as well. Then I'm going to go to the next layer. But what I want you to remember in here, you don't have to, but this is recommended. compare this one with the first layer. What's different in this layer? Why do you think actually we are doing it? We are increasing the number of filters in here, right? Well, why? We're gonna learn more features. We're gonna become deeper and deeper. In order to make the network deeper, usually we go with the 8, 16, 32, 64, and so on. At your own time, if you want, try to put it at 8. It's still network, try to learn, but it become quite slow in terms of learning because your feature doesn't become advanced. Why make the filters basically bigger? I get more representation of that image, right? You can also put it as a 17, 18, doesn't matter. But usually, logically, we go with the 8, 16, 32, 64, 128. So make the layers deeper, deeper, and deeper. After that, same as before, I end up by having so many images. I'm gonna basically use a max pooling to simplify that. I'm gonna go for the third layer. We started with the 8 filter, we went with the 16, we went with the 32. A CNN, as this is based on my experience, this is what the state of art is saying, according to the literature, should have minimum 3 deep layers. If you design a CNN with 2 layers, probably you don't get enough time to do it. Remember that 7 example was these 2 numbers first and the edge. And it took 3 layers to be able to find those layers. But 3 is minimum. If you want to do it, especially this is what, for instance, for FSL last year was saying, try to aim for 7 to 9 layers. 7 to 9 layers usually give you good number of layers to be able to actually to detect if you want to make basically a network from scratch. But 3 layers would be, in this example, would be sufficient. And then I have all those knowledge of learning the features. I need to bring that knowledge back to the fully connected layer. And why should you use the fully connected layer of 10? Absolutely right. I had 10 categories of images. I need 10 outputs in here as well. And then a softmax layer, which is like a normalization, and the classification layer.
So the last layer, now max pooling.
No max pooling. So softmax in here technically does like a max pooling. It's like a normalization. And so what I will do, I'm going to copy everything from here. And this is, by the way, the multi-million pounds architecture of the CNNs, which, for instance, for Tesla is confidential. The beauty of it is just this. Their network architecture, which each company has a really unique one. And we're going to get access to the really well-known one that even Google use, which they were kind enough to publicly allow people to actually get access to those. And I will talk about it after the break. So I'm going to put all those, and this become basically my layers. You see these layers? This has become my network architecture. Input layer, conv layer, batch normalization, redo. Max pooling, conv layer, batch normalization, redo, max pooling, and so on. Right? And after this, what I'm gonna do, I'm gonna start basically learning. What I'm gonna tell the network, you already have an input, you're gonna have your network architecture by start to learn. But now the computer asks me, how fast should I learn? Right? And this is where these training options come in. These are the most important stage of neural networks, right? Architecture is really important, but with the architecture, you can come up with a situation, you get 10%, 20% accuracy. And the beauty of optimizing it is optimizing these numbers. This can easily change the 20% to 80%. So what is going on in here? It says, let's say you have a basic module that is going to go to the exam. Is going to be like a handbook of 1,000 pages, right? Now, in the lecture, I'm going to go to the 1,000 page together in one lecture. Would you be able to perform well in an exam? No, right? If I go on each week, I'm going to give you, let's say, 100 pages into the 10 sessions. Probably you will have good information to be able to actually learn it. But if I go in each lecture, I'm going to go with one basically page, and I'm going to basically rather than a 10 weeks of lecture, I'm going to have 100 weeks of lecture. What happened? You become bored, right? Because it's quite slow learning. Similar things happen to the neural network. This is what we call the initial learning rate. How fast the network needs to learn. If you go really fast, the network doesn't have enough time to learn. If I go really slow, network become lost. What does it mean? I'm gonna, let's say I have 1 million images. I'm gonna feed one image at a time to the network. Let's say this is it, right? Because it's too much. So first, if I had, let's say 10 images at the same time, 10 images of these, but let's say can become interested in the roundness, become interested in the height. But now I'm gonna give it basically one image at a time. I'm gonna do it 1 million times. What it does, first it's gonna pick up the shape with the roundness and the size, and then become interested to reading these, become interested in the color, but this is not what you're looking for. So network become distracted. This is what we call overfitting. So then there is another thing, it's called max epoch. You know what the epoch does? Absolutely right. So you basically, let's say I went through that 1,000 pages to get on the lectures. Once, you're gonna need revision, right? How often? Oh, sorry, not how often. How many times you're gonna start from beginning? That's the max epoch. Coming up with that number is a trial and error, is an experience. So you basically start with the 1. You'll see that the network didn't learn, but the network is going up. I will explain it once we actually showed it how it works. Probably gonna need more and more and more until you're confident network learning. So let's say I'm gonna teach something which is complex to you. I'm gonna put the revision as much as I can till you say you're confident to do it. How I do it? I need to get the mini quiz from you. And that mini quizzes is validation frequency. How often you're gonna have a mini quiz? I will keep getting that mini quiz, which is 30 iteration in here. Every 30 iteration, there is a mini quiz. I keep getting mini quiz until you perform well in that mini quiz, and this is what I say I need to stop. So always there's a relation between the accuracy and the validation frequency and the number of epoch. What I usually do, I'll bring this one low, I'll bring epoch high. So I put usually epoch as a 30, and I know after a period of time is best of time. You're performing well, so I know where to stop. Once I let the computer do the calculation, I'll show it to you. The numbers you need to remember: initial learn rate, epoch, and validation frequency. Try to make sure you need to define it, and these are the 3 numbers you need to play with. So most of the PhDs time, or when you're MSc student, most of the time that you need to spend is not to make it on that architecture. You need to be in front of computer, keep playing with these numbers until you get a really high basic accuracy. And that was what I was doing in the 4 years of my PhD. But now at the end of today, I'm gonna show you something that you don't need even to do that. It's computer automatically gonna optimize it and tell you these are the best numbers, which we call it the optimizing the hyperparameters. So I'm gonna copy these. These are the information. We're gonna put it there. And these become my network settings, training options. And if I go with the training options, you will see these are the network training options. You don't need to worry about these. The only thing, as I said, the initial learn rate, maximum epoch, and also mini batch size, which we will talk about later on. But mini batch size, I think it will confuse you if I go to it. So let's go with these. And now I'm gonna let the network to train. In order to train it, I need to say net train network based on my training data, based on my network architecture, and based on our training options. Always in the training, you need to have these 3 values. And I'm gonna let it to run. In here, probably if you have a really advanced network, this is where you can see the fan of the computer starting to actually do all those calculations. You can see still his MATLAB is busy, haven't started yet. Here the fan of my computer. As soon as you put it, this is where the computer start. Depends on your computer. Sometimes your computer is completely freeze and you won't be able to do anything. So if you're doing a project with me, if you're using your own computer, don't use the computer at the time. You most probably won't be able to even use it. It keep crashing if you're gonna touch it. Because now we're gonna keep applying those matrices on every single pixel of that image. My computer has a GPU, that's why you went with a GPU. If your computer doesn't have a GPU, you're gonna go with a CPU. So this is, to be honest, if I had this in my first year PhD, I was really happy. This is ideal training, ideal, because the results are basically are diverging, not converging together. What happened? Network is keep trying to learn features, have mini exam. Do you remember the validation frequency? Every 30 iteration, these are iterations, have a mini quiz and a mini quiz and a mini quiz. In each mini quiz, it already has a solution, right? Because we give the 10,000 images into the 10 category, already has a solution. But that image is unseen and never seen it. Out of, let's say, 75% of that image, data has been seen, 15% wasn't basically seen. 25% wasn't seen, right? So what that 25% because it already has a solution, check it. If it match, it's fine. If it doesn't match, it reports it in an error. My network is learning in here, right? You see that my network is learning. But have a look at it. What was the epoch? How many times we're gonna start from beginning, right? If I switch off, if I put epoch as the, let's say 1, what was my network accuracy? 70%, right? 70 something. So I allowed the computer to go and learn another time with the epoch 2, 80 something. In the epoch 3, reach over 90. So what I could do, I could go with the epoch 10. It takes so much time to train, but I know where to stop. In here, if I want to stop, probably epoch 3 or epoch 4, you don't learn anymore. It's just a waste of time. So I could come back and say epoch 3 is fine for. Network accuracy is 98. What was the MATLAB one? I think we even got more than MATLAB. What was that MATLAB guy by the MIT, by the way? What was the accuracy they got? 99. Or they went better than us. Usually each computer has around 1% difference. So if you're using it for your project, if you're gonna write a paper, you have to tell them what is the exact computer used. Configuration. You have to put the graphical card, you have to put how much RAM used, because a random number, random calculation. So in that calculations, depends on which images they use to apply that number to classify them. You get usually around 1% different. What was the accuracy you got? Oh, you increased the epoch? Okay, good. What did you get? 98? 98, yes. So let's go through, and by the way, you can now export this image. This is what we call a training plot. Before MATLAB didn't have an export option. You had to picture a screen, but now they added that option. So, and it took 19 seconds. What's ideal work? You're gonna reduce that time, and you're gonna see my MSc students, these training can be few hours for you. My PhD one, each simulation was taken over a week. And then I realized that actually my system doesn't learn, so I had to kill it. I had to start it again. And that's why I moved to the clusters. If you're dealing with a terabyte of data, you're dealing with the 1 month's training. So this is really simple features learning. That's why it was 19 seconds. But computer to computer is different. And this is where the GPUs play quite an important role. And if you don't use GPU, if you use the, let's say, i5 CPU, probably with your data set for which one was working on the emotion with the trimmer. Each simulation, I think for you takes 7-8 hours. If you use the NVIDIA GPU, if you use 4070, would be, I think, 1.5 hours. And I have access to that computer. I can give you access to that computer, so you reduce the time of training. But that is a big issue, because if you're going to put it on the, let's say, autonomous vehicles, that car needs to have a GPU. That's a couple of grands added on the price of that car, which is why we try to avoid really complex CNN. We try to simplify that CNN. Do you remember last year that car had a delay, huge delay, and that 6 seconds was because of the CNN behind it, which is why I asked Pranjal to simplify that CNN. So, and then if in case you were not happy with these numbers, you can go back and I'll keep changing it. Let's say increase the epoch, increase the validation frequency, which means that rather than 30 iterations, do a mini exam every 10 iteration, so you can see a better network performance. What I want you to do, let's have do you prefer to finish early, or do you prefer to actually finish around the same time? We most probably would be able to finish by 4:30 if you have a shorter breaks. If I'm gonna give you lunch breaks, we should finish, let's say, 4:35. Which one do you prefer? Having a lunch break or having a shorter break? Shorter break? Shorter break. So shall we have, let's say, 15 minutes break right now? Come back here. And 15 minutes is okay, or do you need longer? 15 is fine?
Yeah, good.
Have 15 minutes break, come back here, and then we'll go through. And this time we don't want to use codes. Good? Great. Yeah. Make sure you get some fresh air, and we'll back here.